Oh no, sorry about that, Evie. I forgot to unmute myself. That's a terrible mistake. So just for a quick rundown on what I was saying there, our upcoming number at quiz 7 is going to be due tomorrow. Quiz number 8, and again, sorry for muting myself. Quiz number 8 is a pretty pivotal quiz because it's going to be based on the chapter 10 material, which doesn't have a MyLab assignment. So the quiz down below is going to be our main practice for getting through the chapter 10 problem. And because I didn't put down a MyLab assignment for chapter 10, when the chapter 10 problem comes up on the third exam, it's going to be very, very close to what the quiz 8 looks like. I'm pretty much just going to change the context and then the same kind of questions you can expect for the exam. So practice on quiz 8 and you'll know just what to expect on that problem on the exam. And the last thing I mentioned before I discovered I was muted is we're just on the last part of section 13.1. But any questions or comments at the moment, folks, before we get started today? Okay, so we're almost done with week 10. That means there's really not a lot of the semester left to go. We have a 16-week semester, but 15 weeks are the actual instructional weeks. We're 2/3 of the way done with the entire semester in those terms after this week is over. So we're definitely getting through it. We're seeing some of the trickier stuff so far in the semester, but keep working like you've been working so far, and we'll get through the rest of it just like we have before. It might look tricky, but the way it goes together is the same similar kind of stuff. So here's a big theorem in terms of trickiness, but when we examine each of the parts in turn, really all we're talking about is a particular kind of normal distribution. Let's pull up a quick visual. We've seen normal distributions before. This is from section 5.3, when we were thinking in terms of the empirical rule. The mean of the sampling distribution is P, just tells us the true proportion, whatever it is the dead center of the normal distribution. We also know what the standard deviation is going to be. It's going to be the square root of P times Q divided by N, where P is the true proportion, and Q is just defined to be 1 minus P. We are going to look into section 13.2 for guidance on this part. And the last statement of the central limit theorem is that the statistic P hat, the sample's proportion of successes, came from the normal model. So that's the big idea of the central limit theorem. That means we can start using the TI-84 calculator and the normal model together to start answering questions related to approximating the parameter P itself. To get there, we also have to remind ourselves that, let's put this down on paper. One big reminder in statistics is we make assumptions what the parameter P is just to practice with the central limit theorem. But in actual statistical practice, that's the thing we're trying to estimate. We don't know what it is. We just made the assumption for the sake of working through a problem. So here's our big challenge in statistics. In practice, the parameter, let's add all the parameters on here. Parameters U, population's mean, sigma, population standard deviation, and P, the population's true proportion or percentage of successes, are unknown. And that's the whole reason this course is 16 weeks long. It's our job to estimate them and give a reliability error on that estimate. So that means we don't know what P is right here. That's an unknown. And it gets even worse. We don't actually know the true standard deviation because, well, it depends on P. P is part of the formula here. Q is just 1 minus P, so it's the second part of the formula. The standard deviation is also unknown. That makes the central limit theorem feel kind of useless in a certain sense, but we can still salvage this and put down a pretty good statistical method. If we don't know the standard deviation, we still have a good estimate. The idea is, even though P is unknown, we can still approximate that P is approximately equal to the statistic P hat. And that's what the standard error is all about down here. The standard error of the sample proportion P hat is given this symbol, SE for standard error, parentheses just mean literally of P hat. it's this interesting formula here, and its whole purpose is this is approximately equal to the standard deviation of p hat, the thing that's the unknown, to the standard deviation of p hat. So even though this is unknown, we can put down a pretty good estimate of this quantity and use the estimate of this quantity to come back and estimate p. We'll see how this works in sections 13.2 and 13.3 when the whole procedure goes together. But the new big object is this, standard error of p hat. There's lots of different standard errors in statistics that we're going to look into. For example, say if we're in maybe chapter 15, we'll be looking into something called the standard error of y bar, just a different statistic, a different kind of standard error. This one's not so bad if you're curious. This one goes S, the sample standard deviation, divide by the square root of n. So we'll look into that formula later on. Our formula is a little bit more complicated. It goes p hat, 1 minus p hat divided by n, all square rooted. And it might feel like we've practiced it before, but not exactly. We didn't put the statistic down there. We put in the parameter. We assumed the true proportion was 0.53, and we said if that's actually true, what is the standard deviation? 0.0499. But we have to admit, we don't actually know the standard deviation. We're going to just estimate it through this object right here. So that's the central limit theorem and its limitations. And what we can salvage from it is the standard error to use it to start making estimates. That's what example 3 is going to be all about. And any questions at the moment with the ideas so far? Okay, so to practice with all this, that's going to be the purpose of example 3. It's a pretty short set of context, but it's more informationally dense than it seems at first glance. Let's put in a little spacing here in case we need it. Let's read this really carefully. After hearing of the national result, 44% of students engage in binge drinking, and it's defined here in the parenthetical, 5 drinks or more in one sitting for men, 4 drinks or more for women. So 44% of students engage in binge drinking is the national result. I'm not sure what this year this is based on. I think it's kind of just made up context. That's kind of seems plausible. A university administrator, after seeing this result, surveys a random sample of 244 students at his college. So far, we can say N is 244 students by this information. So that's the sample size that goes into this part of the formula for standard error. Found that 96 of them admitted to binge drinking in the past week. So out of the 244 students, 96 of them seem to fit the thing that we're interested the most about this study. So even though it seems kind of counterintuitive, what we would say is there are 96 successes, where a success is the outcome of admitting to having binge drink in the last week. It'd be nice if we knew when the study occurred, if it was a real study. You could imagine this would be a different number depending on if it was before, say, maybe the World Series or something like that, or is it during March Madness? Probably you get different kinds of numbers for this kind of stuff. So that's the situation so far. Let me kind of target this parenthesis a little bit better. We have 96 successes admitting to binge drinking. Sample size is 244 students. But here's what makes this problem really kind of confusing to think about. There's 2 populations at the same exact time that we're dealing with. There's the national population, for which the result is 44% of successes. But that's not what we're studying. That's just something we're comparing our results to. The university heard about the national result. That's population 1. So this is one population. One population is, it looks like it's about students. So let's just say one population is all college students. in the nation. But that can't be the actual population we're using. The reason is, where did our sample come from? The university administrator at a particular college, just one college, say ISU, just for the sake of an immediate context, sampled 244 students at his particular college. That's now a whole new population. It looks like the population we're really studying in this problem is all the students at just this one particular college. There are 244 students, 96 successes, and we'll study that information about this college. Law statistics problems kind of go like this, where we're comparing multiple populations at the same time, and it makes this figure 44% pretty confusing in the problem. This 44% is a parameter. It's a parameter for a population we're not even studying. It's not P in this problem whatsoever. P is a true unknown. So let's just say here, just to be specific, the population of this problem is all college students at this one. They said a university administrator at his college. We could just say university or college, I suppose. It seems like that's interchangeable. At this one university. So again, you can imagine maybe this was a study where it was 244 ISU students. So that's the major confusion about the problem so far. It's always good to read these a couple times, see if there's layers to the problem, if there's multiple populations we're comparing to at once. Any questions or comments about the context breakdown so far? Okay, well, if we do just a really quick calculation, we're not going to answer part A, but just if you're curious, why would the university administrator want to do another study if we have a national result of 44%? Well, maybe we're wondering if our university is higher or maybe lower. Who knows? So once the administrator got this data, they probably went like this: 96 divided by 244. This is the percentage of the sample of students at this one college that admitted to binge drinking. It's 39%. And the administrator might have celebrated and said, hey, that's below 44%, but you can't celebrate at that point. The administrator would have been doing this, estimating a parameter through the statistic. But there are sampling variabilities there. There's unreliabilities. Until we describe the margin of error, this 39% might not be statistically significantly different than the 44%. There's just variability that makes us get different values every time we get a random sample. Our college could be the same or different from the national result, but statistics are going to be what addresses this question. We'll put down a margin of error to making this estimate right here and see if we're really below 44%. To make all that happen, we need the standard error, and we also need to say exactly what we're talking about by describing the unknown parameter P. This is tricky, so just for the sake of doing this one more time, we won't do it this way every time, but if you like seeing this as a structure, come back up to this part, because this answers the question of what is the parameter P every single time. It's a great way just to put these ideas together. Part A is a tricky problem because we have to know what exactly is the population. That's already pretty tricky in this problem for reasons we've discussed. And you have to know what the success is. So we have to be very fluent of just exactly what's going on with the context. So let's erase this part and write in what our successes are. We read it through because admitting to binge drinking keeps on coming up, and that was the second number cited in the sample. This is what the successes are going to be. So we have P is the population proportion of students admitting to binge drinking. It said in the past week. I'll just say last week for short. kind of barely squoze that in. And then P is a population proportion of students admitting to binge drinking for all not university students. That's talking about the national result. We just said P equals 44% or 0.44 if we were talking about them. That's not our population. We'll have to say for all college students at this one university, because that's where the sample comes from. The sample came from one university, and the sample always comes from the specific population. So for the population in the context, we'll say for all college students, at this university. So just putting down those or identifiers, this was the population that we filled in, and this was the notion of a success that we filled in that first blank. Well, this is often the trickiest part of these kind of problems. And the context being short doesn't mean it's easy to kind of tease out what the parameter ought to be. We really have to think about it deeply, see if there's layers to what's being described, multiple populations like in this one. And that's what made describing the parameter P pretty tricky in this problem. Any questions at all, folks, by nailing down this parameter? Okay, the questions are pretty tricky in a certain sense. Unknown parameter P, you had to know that you're describing the population proportion, or you could have said percentage here. Part B is pretty tricky too. It's kind of like a vocabulary question in a real sense. When it says the sample proportion of successes, we have to know that what's being mentioned here is really P hat. All we're doing is computing that value. P hat is calculated by taking number of successes and divide it by the sample size. But again, it's a tricky problem if we're not sure on the language. So this is how problems would be written down as, say, a quiz problem, an exam problem. They come up this way in MyLab statistics occasionally as well. We have to know that we're referring to P hat by that language there. But once we know that, the hint is if it mentions successes, we're just throwing the 96 successes up into the numerator. Divided by what we said the sample size in is, that's n, 244. And that's P hat. I didn't say anything about rounding on this. Let's add some information about rounding. Sorry for this quick edit. Typical rounding that makes the most sense for these kind of problems is usually 4 decimal places. So let's put here, round to 4 decimal places. Okay, so anything in red that you noticed in the notes were just things I forgot to put into the problem. So there's another quick edit for this one. So the 4 decimal places will have 96. Well, we kind of did it already, didn't we? It's all right here. You could go times 100 and turn it to a percent, but the best advice here is definitely don't do that. When you go to use a standard error formula or any other formula whatsoever, we're always going to use this as a literal proportion, not as a percentage form. Putting the percents up in this formula would give us a very wrong value. So we'll put in the value 0.3934, which we can interpret as saying about 39.34% of the sample admitted to binge drinking in the past week. Okay, so we've got through really the major part of the context. We said exactly what our parameter is, as we discussed it here. This was just the population. The parameter involves these successes. We've calculated the statistic. We did that once already up here when we were looking at the data. Part C is where we start to use the central limit theorem. So let's take a look just by taking a quick screenshot on this one. It says, what is the mean of the sampling distribution of P hat? Well, the sampling distribution of p hat is described by these three different rules. The sampling distribution is approximately normal, it has a standard deviation, and it has a mean. So when it says the mean of the sampling distribution of p hat, that whole statement is referring to p. Making this the trickiest question ever. That's the whole answer. You don't have to rewrite it's the population proportion of students admitted to binge drinking for all college students at this university. We've already said what P is. The only way you can miss this problem is putting down, say, 0.3934. That's the sample proportion of successes, not the mean of the sampling distribution. And another way that's easy to make a mistake on this one is it's not 44% either. We don't know the value of P, so we should say here, just as a reminder, P is unknown. In other words, P is not equal to 0.44 or 44%, however we set it. That's what makes part C kind of tricky. And it's just a reminder that P is unknown. We can't actually put a number there. The job of the university administrator is to estimate this value P in the first place. Well, we've got the mean though, it's P. We just know how to describe it. We know it's approximately equal to P hat, but there's more to that story. We have to describe the error in making that estimate. And so that's where the standard error comes in next. First, any questions at all with part C? I feel like it's kind of a weird question out of nowhere. Okay, so to give a good estimate on P itself, we need to know standard deviation. So to do that, we can't compute standard deviation exactly, but we can give a great approximation. Like we mentioned, the great approximation to the standard deviation is this thing, the standard error of P hat. It's another basically vocabulary kind of question. When it says standard error of P hat, we have to know that we're talking about this symbol, SE, P hat. But more importantly, we have to know we're using this formula. By formula, it's the square root of P hat times 1 minus P hat divided by sample size n. So that's our formula we're going to use. It's the one up above, but instead of scrolling up and down, good strategy here is just to write it down on paper. You can put it on your notes for exam 3, but the more you just write it down, the more you'll memorize it, the more familiar you'll become with it, the easier it is going to be to use. It's just another calculator computation, standard error P hat. We computed this way. We're going to make two substitutions. In place of where you see the P hat, those two positions, throw in 0.3934. So 0.3934 would go here. 1 minus 0.3934 goes here. It's a lot of writing. Then the whole thing is divided by the sample size n once again, which was the 244. At this moment, we're throwing into the calculator. This one, like we mentioned, it's not as bad when you're doing it on a quiz or exam, but it's finicky when you're doing it on WebAssign because we have to get this down just right. And if they say to round to 4 decimal places, as we should have said here, then we also have to round right. If we round incorrectly, we could lose the whole question, even though we put it in the correct calculator exactly. So these ones tend to be frustrating. Go slowly, carefully. Here's a strategy I would personally use, and let me know if you're getting anything different. I would go outside in. These calculators we have are just really convenient of typing these in verbatim the way you see it on paper. Hit second, the power 2 button here to the left and up from the number 7. That gives us the square root, and we can just type in the numerator as one line, exactly as you see it. 0.3934. Make use of the parentheses if you like, or you could use the multiplication button. Either way is a fine way to put it in. Hang on, I should redact that statement. You can't use the multiplication button right here It has to be a parenthesis because that's an entire group. If we did times one, the order of operations would get tripped up in the calculator. So parentheses are required. We'll make a comment of that on the notes. 1 minus 0.3934. Then you have to close the parenthesis and go division by 244. It's a long computation, so these calculators tend to scroll to the right as you keep on going, and it gets longer and longer. If you need to see the whole thing, hold the left key, and it'll go to the beginning. Hold the right key, and it'll scroll back to the right-hand side. So let me hit enter on this. Make sure your 244 is inside the square root symbol. And you get this as a result. Does that look about all right to folks so far? I've got a 0.03127. So I would round this to a 0.0313 to 4 decimal places. Awesome. And again, we've made a big deal of this before because this is a super frustrating problem in MyLab statistics. When it says to round to 4 decimal places, as we just baked into the instructions, we go to this position. And if you put this in MyLab statistics, 0.0312, we miss the whole question. We get to try again, but that's really frustrating. It rounds up because the next value is greater than or equal to 5. So just for another concrete reminder on that one, I'm not that picky on paper for quizzes or exams. If you gave me a 0.0312, I wouldn't take off credit for a misrounding, but MyLab does. So let's put in 0.0313 just to be careful. Well, any questions at all, folks, on getting that number out? Anyone get a different number or want to look at it from a different point of view? Okay, I would say this is probably the easiest way to put it in your calculator, because if you make a mistake on a digit, you can hit the up arrow, hit enter, and just fix wherever the mistake is. So that makes it kind of convenient. I actually can't put a screenshot of this down on the paper because it's in a couple spots, right? So this is what it should look like in your calculator. In the TI-84, you'll type in something that looks like this. 0.3934, 1 minus 0.3934, division by 244. So about like that. The two things that are the very common mistakes are, and again, redacting what I said earlier, you really need those parentheses if you're typing it in this way. So that symbol is required. Make sure you open and then close the parentheses in those specific spots. And the last easiest mistake to make is make sure 244 is inside the root. That's visually an easy mistake because if you do this, go division by 244, maybe you're a little tired. This looks pretty correct as well, right? But it's a mistake because the square root ends right on that parenthesis. And here's what the effect would be. Totally different number. It's way, way smaller now. So just make sure 244 is covered by the square root symbol, that you didn't kick it outside, and you're going to be in great shape. Another big reminder, this is going to be an exam 3 question. On an exam setting, it's easy to make a simple mistake, but if this is on paper for exam 3, as well as for the final exam, then this is most of the credit. In other words, if I just made a mistake and put in 0.002 right here, if it was a 4-point problem, I'd probably give you 3.5 points out of the 4. Because you know how it goes, I'll just assume you were stressed out on the exam. It's easy to feel a little bit stressed out. Maybe you just had a fat thumb that day and you just hit the wrong key. All sorts of weird stuff can happen in an exam setting when you know the concept just fine. So make sure you have it down on paper. That's where all the partial credit comes from. So the question now becomes, what is that? What is the standard error? We're going to explain it, what it means using the context. And this problem right here is similar to a my lab problem as well in the homework. It's tricky because they give you a multiple choice problems a lot. And this is one of those concept questions that is multiple choice, where there's just like one little thing that's wrong in different versions that gets you to the right answer. Here's what you'd be looking for to get the real interpretation of the standard error on this. We would say the sampling distribution of p hat it's a long statement, but here's another look at what we mean when we say standard error. The sampling distribution of p hat for the sample proportion of students that admit to binge drinking so that was the successes in this problem, and p hat is just a statistic we're using to measure it. That's the 0.3934 that we were computing. But we're talking about, when we say sampling distribution, we're talking about this thing, the normal model for where p hat actually came from mathematically. We can say has a standard deviation that is approximately 0.0313. So this came from the standard error itself, but the other element of it is it depends on the sample size. If we took a smaller or larger sample, it affects the standard error as well. So we have to put into this write-up for a sample size of n equals, well, probably there wouldn't be an n equals, let's just say a sample size of 244 students. That's a pretty long and abstract statement altogether. I don't think this is a really good question for a quiz or exam, to be honest. It's just another way to think about the standard error. It's probably one of the trickier questions in the actual homework system for my lab. It allows us to at least think about what is a standard error one more time before we go into the next section. Well, we did it, folks. These are the major things that we're going to be studying when we look into a sampling distribution. There's a lot to think about and discuss in this section, so it's a good one to kind of revisit, reread, take a look into the formulas and the comments of the author to see what's going on there. In the next sections, we're going to see when is the sample size large enough for the sampling distribution to really be approximately normal. And the 13.3 section, we put everything together, the standard error, the normal distribution elements from it, to compute the confidence intervals. Any questions or comments at the moment with what we've done so far? Okay, well, this section is horribly abstract in all honesty. So it's good to kind of just wrap this up by saying what we've done so far. Let me put a little border here just to indicate this is whether the problem ends, but this is what we have at the moment. We put down a pretty specific described parameter P right here. In this study, we have that thing that we want to estimate. We can in fact estimate it right here and now. We can say the following: P is approximately equal to P hat. And we computed P hat several times. It was, let's just cite the number, 96 successes out of 244 students for 0.3934. 0.3934. But this takes us back to the first day of class where we've mentioned over and over again Any estimate like this, whether it's a population mean, a population proportion P, it's useless unless you can describe the error made in that estimate. But we have a standard error. We compute it to 0.0313. We can do that right here and now just to put all these concepts together. So we go back to the sampling distribution. That's the approximate standard deviation of the sampling distribution, 0.0313. Let's pull up this. I guess it's a slide at this point one more time. This is the empirical rule. So it's an approximation, but all we need right now to connect our concepts is a good approximation. What did the approximation tell us? It says approximately 95% of the observations are within 2 standard deviations of the mean. Well, what do we say the mean is? The mean of the sampling distribution is directly P itself. That's the thing that we're trying to estimate right down below right here. So our mean in this problem is P. Let's see if we can throw that in here with the annotation. P is the mean. This is directly coming out of the empirical rule. And we don't have the exact standard deviation, but we have the next best thing. The standard deviation let me put a box around it. I think that makes the most sense. This standard deviation is approximately the standard error of P hat. And we found that to be 0.0313. So we have a known quantity to estimate with, the 0.0313. P is the unknown. But when it says 95% of the observations, there's another object here. This is the abstract part of the entire central limit theorem. When we go to calculate a study by taking a simple random sample of 244 students, the things P hat came from this normal curve. So when it says the observations, we are talking about P hat itself. Deserves a bit of an exclamation mark because that's a humongous connection we're making all at once. Let's use the empirical rule right here and right now to make a big conclusion. So dropping down to the statement we're making so far, this probably deserves a new page. Let's put it down below here. We have a parameter that's an unknown, a true unknown. We have an approximation, but the central limit theorem tells us P hat came from a normal curve, and the observation P hat is within 2 standard deviations, approximately that standard error, of the mean P, the thing that's unknown. So we can now say this, an approximate. We're going to use this line right here. We could have used 68% or 99.7%, but higher level confidence is more typical. We'll say an approximate 95% confidence interval for P is, we take P hat. It's within 2 standard errors approximately of the unknown. So we'll take P hat add or subtract 2 times the standard error of P hat. This is going to give us a whole interval of numbers, but it's just taking the empirical rule together with the central limit theorem and connecting a lot of ideas, but all of them directly together. So the distance that P hat is away from P is this quantity. Let's compute it. P hat is given to be 0.3934, so directly substitute it up from here. Add or subtract 2 times. We'll give a more specific number than this one. And if you've seen statistics before, you might know the number 1.96. Seems to come up a lot. 2 is pretty close to that value. And we'll compute our 1.96 ourselves when we go into section 13.3. It's 2 times the standard error p hat. And the standard error was the 0.0313 we see here. This gives us a range of numbers. So let's do both of the computations. P is going to be within this range. So we can say it goes like this. P is bigger than or less than 2 specific numbers. Going into the calculator, let's clear off all this extra noise. I want to put in this entire line, but use the negative sign first. 0.3934 minus 2 times 0.0313. So this gives us the lower bound in our estimate, 0.3308. 0.3308. Then we do this whole computation again, but this time we're using the plus. Big shortcut here is just to go up arrow, highlight the formula you just put in, enter drops it down, and left arrow over here to just flip over to a plus. Speed gives you more accuracy by doing that kind of thing so that you don't accidentally mistype something. We get 0.4560 if we keep 4 decimal places, 4560. So these are our values for P so far. But what was P? It was the true proportion of students at this college that admitted to binge drinking. With 95% confidence, that unknown parameter P is between 33% and 45.6%. So if we change this to percentages, this is 33.08%, less than P as a percentage, 0% symbol just as a reminder, is less than 45.60%. The p hat above was also a percent if you preferred the percent point of view. It was 39.34%. And notice how big this range is. Even though the sample was large, there was a humongous amount of error when we made this estimate. In fact, we could say what the error is specifically. This is called the margin of error. And it's this part right here. The thing that we had to add or subtract is the margin of error. The margin of error in this problem is approximately 2 times 0.0313. Let's multiply that out just to get a value. 2 times 0.0313. It's 6.0626, which means as a percentage, the error in estimating right here has an error as big as 6.26%. So that's pretty wild. That's a humongous error altogether. But at this point, we're doing real inferential statistics. We took data from the sample, p hat is 0.3934, and we related it to something that was completely unknown, the parameter p, just through the good old empirical rule. We'll make this even more accurate when we put a better number here instead of 2, like we were mentioning before. But this is the whole punchline to chapter 13. This is what inferential statistics looks like. And if we go back to the very top of this problem, remember the national result was 44%. The university administrator was interested in that and took a sample of 244 students at his own university and found only 39.34% admitted to binge drinking. Some people might have reported on that and said, our university is doing better. We have good evidence that less students binge drink at our university. Go us, go ISU maybe. But that would have been a really, really embarrassing statement because the margin of error is so gigantic, 6%. Our true range for estimates on the unknown percent P, recall P is the percent of students that binge drink at our university, is at the high end, 45.60%, exceeding the national value. There's humongous range here. We don't have any evidence at all that our university engages in binge drinking less than the national value. It could even be higher. Yeah, go ahead. Yeah, that's a good point as well.
The fact that we.
It is, yeah. So the way they did the study is really particular. You couldn't have, say, like the president of ISU interviewing people because that would set the stage for something. You probably want a peer asking you the question, right? And what's even worse is you had to have a random sample of the 244 students, but you better not put them all together and ask them the same question at once because people are going to start mirroring other people's responses and it could fluctuate like completely randomly and wildly at the same time. So, yeah, that is a good observation right here. This isn't even the reality of who really binge drinks. This is the reality of if you do a study a particular way, who admits to it, who could be lying, in fact, who knows what's going on here. So it gives us some idea of what's going on, but getting the actual reality is extremely hard here. You might have to go into just other kinds of ways of figuring this out. But other questions or comments at the moment? Thanks for mentioning that. That was a great observation about this.
The two that you got, is that because it was within two standard deviations of the mean?
Yeah, exactly. So those twos here, they match up. Circle that one here and that one here. So if we wanted a different level of confidence, usually the lowest level we go for is 90%. And this is closer to like a 1.6. 95% is in the middle of the line. And this is a better estimate is a 1.96. And if we go for something like a 99%, this becomes like a 2.6, quite a bit higher. So there's still a lot of stuff we have to talk about. What exactly did we mean by 95% confidence? What's a good way to write this down as an overall conclusion? But at the moment, this is the major punchline. This is the reason we studied the normal distribution in the first place. We actually aren't so worried that the normal curve describes certain things really well. The major reason we care about the normal distribution is that it shows up in statistical inference all over the place, even with this, which was categorical data, a huge surprise. Oop, didn't mean to do that. There we go. So the next thing we're going to look into in section 13.2, it's all about what are the actual conditions so that a conclusion we make here is as sound as possible. In other words, how do we know when the central limit theorem is actually working? The empirical rule came from this part of the central limit theorem, and it has conditions and has to be large enough so that when p is close to 0 or 1, we can still get approximately normal shape. We saw cases where that didn't happen so easily unless n was very large. This was skewed to the extreme left when n was, say, around 50, for example. So let's take a look into section 13.2. Once this saves, it'll take it a moment. 13.2 gets us really close to our official procedure in 13.3. All we're really doing as a major goal here is checking conditions. So here's the central limit theorem brought back to life in this section again. It's the only big idea that we put in a box because it's, again, the biggest idea in this whole course and just about any statistics course. And when we're estimating it or using the central limit theorem for proportions, here are the four conditions that have to be validated. Independence, randomization, the 10% condition, and the success failure condition. If all four assumptions work just right, the conclusions we would have given, say just on the very last problem we looked into, would have been very sound. Some of these are very tough to check. Some of them, they're not too bad to check on paper. And on paper, we're going to specifically check conditions 2 through 4. So conditions 2 through 4, these are the ones that we check. We check conditions 2, 3, 4 on quizzes and exams. So condition checking is tough. The first one is the independence assumption. The reason we don't check this condition is really the only way to check this is you had to have been the person that came up with the study. You had to have been the one who designed how the randomization is going to work. You had to have been there from the start to the very end when you got the data to know if this was violated or if it held. What this condition says is the individuals in the sample must be independent from each other. And thinking of just the last problem, you can see how independence could have went wrong. If we took a random sample of 244 students, but took, say, groups of them, even just groups of 2, ask people the question, did you binge drink last week? We violated independence in a big way because one student answering that question can influence the other student. Other ways independence is violated could be things along the lines of contagion. If we're studying something contagious like chickenpox or something along those lines, we take a random sample of people who may or may not have a contagion. We have to know that those people in the sample are isolated each other, totally isolated. Otherwise, someone having the thing you're trying to study can affect other people in the sample, even though they may not have had the condition when you came into the sample from the beginning. So this is, again, fantastically hard to check. Studies get published in journals all the time where people just found out after the fact, sometimes years later, the independence actually never held for these really fine, minute technical reasons. It's not our job to discern independence because when we look at the context here, we're just not given enough information about that. We would have to have a study like this one where you go to the Lancet Journal in 1974 publication, you read the whole entire thing, and then you have an idea, was independence reasonable? And that's still, you're only making some best educated guesses. So it's not something we can really address fundamentally in a whole concrete way, but it's still stated here just for the sake of completeness. There's ways your study could fail, even if you felt like you did everything right, because someone in the sample might have influenced the outcome to someone else in the sample. So the independence assumption is the most vital thing to watch out for. There's one thing that can somewhat help us with independence. It's by no means a guarantee. But if the data come from a simple random sample, in most situations, that already implies the sample is independent. So this is something we're going to check from the wording of the problem. This problem might say the study was random. If it does, this condition is met. But we're just looking at really short abstracts. It doesn't necessarily say everything about the study. If it doesn't mention randomization, then we'll say that this is an unknown. If we know that they did a study in a way that it wasn't random, we'll say the condition fails. But we can check this one, and just a quick comment. The simple random sample often implies independence. Independence is vital, and that's what the next condition is all about as well, the 10% condition. But any questions at the moment so far? Okay. The central limit theorem for proportions is a kind of a weird theorem. The formulas that you see here, like for the standard deviation in particular, come from weird places in probability theory, something called the binomial distribution. The binomial distribution also requires independence, and it can fail in a different kind of way. If your sample size is too large so that it exceeded 10% of the entire population, independence is broken in a different kind of way. And the central limit theorem suddenly just doesn't work. So this one is also about independence, but it's kind of more abstract. This one we can check to some degree. And this is how we check it. It looks really weird. We must argue. You can argue for or against. Just use the best educated guess you have from the context of the problem. if your argument is plausible, and even if it disagrees with another student in the class, you would still get full credit. It's all about making the right kind of connections about what you know about the sample and the population through the context. So you have to argue that 10 times n is less than capital N. That is a weird statement that deserves a lot of justification right there. First, lowercase n is the sample size. Uppercase N is the population size. So we said our sample should not exceed 10% of the population. It turns out that's equivalent to just saying 10 times n is less than uppercase N. 10 times the sample size is smaller than the population size. If that seems like a valid justification to you, the 10% condition is met. Our sample does not exceed 10% of the population. Honestly, that's still really super confusing. The best way to justify how this 10 times n less than n really works, where uppercase N is the population size, is just to rewrite this statement. Our sample, that's n, should not exceed, means strictly less than, 10% of the population means go as a decimal, 0.10 times n. So if you look at this equation right here, well, rather this inequality, n less than 0.10 times n, you can multiply both sides of this inequality by 10. You get 10 times n is less than 10 times 0.10 times uppercase N. 10 times 0.1 is exactly 1. So you get 10 times n is less than 1 times n, which is just n itself. So that's where this comes from. The short of it is we just take 10 times the sample size. And if you believe that's smaller than the population, the 10% condition is met. So it just comes directly out of this wording right here. That highlighting looks kind of funny though. Well, any questions so far, folks, with the 10% condition or the randomization condition? I feel like I should write here as well, just for the sake of making that connection. Okay, last one is the success failure condition. And what that is all about is finally addressing this part of the problem. Let's leave this one in gray. So P can in fact be pretty close to 0, but you have to overcome that by making the sample size n gigantic. Similarly, if P is pretty close to 1, the sample size n has to be large. But the question we have to resolve is how large? The success failure condition addresses that finally. The sample size should be large enough so that the number of successes and failures in the sample are both larger than or equal to 10. If this condition is met, it satisfies this part of Rule 3, and you have a great guarantee that this approximation is going to be well enough for us to use it in statistics. We'll be very close to the normal curve. Writing it out as a formula looks kind of funny. Just recall P hat is the sample proportion of successes. Multiply that by n, and that's the number of successes right here. So this is the number of successes. N times Q hat. That deserves another justification. Recall Q hat is just 1 minus P hat. Sometimes I kind of hate that the author uses Q hat. It's probably simpler to call it just 1 minus P hat instead of introducing another symbol, but at least it's a compact statement now. N times Q hat, that's just going to be, as a formula, the number of failures. So these are the conditions of the central limit theorem that's going to give us a great estimate. So if we did something like we did again in 13.1, where we estimated P, we'll have a great understanding that that estimate is a valid one, that the confidence interval we computed is highly accurate. And just looking into this one more time, so much stuff happened in 13.1 that's good to kind of connect the dots even further. We made some kind of strange assumptions just to practice with sampling distributions, the central limit theorem. One assumption is we took a random problem and we just assumed that the sample proportion of successes is 0.93 just to see what would happen. And we argued, what should the sample size be? How much should it grow until we got something that looked about normal? We settled for a 200 in our sample here. So now we wonder, was that large enough? If the sample size is 200, well, we don't have a statistic p hat. Let's use p just as our closest analogy. We could go here, take 0.93, multiply that by the sample size of 200. This would be the number of successes we would expect to get, 186. Definitely, that's larger than 10. But what about the number of failures we're expecting to get? We would have to take 1 minus 0.93. So 1 minus 0.93, multiply it by the sample size. This is the end part of 200 we selected here. This is the number of failures we would expect to get. And it came out as 14. We should have thought that should come out, right? If you've got a sample size of 200, 186 expected successes, take 200 minus 186, you get the 14 expected failures. We'll actually take advantage of that and possibly not even use this formula when it comes up. But that met the benchmark. It's larger than 10. So we were right to stop right at 200. 200 was a good sample size to get close enough. So at this sample size, we have the statement, sampling distribution of p hat is indeed approximately normal in this picture as well. Sure, there's a little bit of skew, it never disappears, but it's close enough for strong statistical inference. So there's a lot to talk about with the conditions. If this was a problem on exam 3, this is one whole question, really. I would ask you, what are the successes? Do we meet the randomization, the 10% condition, success failure condition? And that's one whole problem. Another whole problem would be just doing the confidence interval, making a conclusion. So we have a whole new problem we're going to take a look into and 5 minutes to give this a try. But any questions at the moment with any of those assumptions?
Could you use that same number for the 10% condition?
Yeah, absolutely. So back in this problem right here, with the 10% condition, we'd have gone like this. We'd have taken on the 10% condition here, 10 times n, it would come out as 2,000. So this has to be less than uppercase N, which is the population size. So this was a while ago, but the reminder is this problem was about social network users on Facebook. And certainly 2,000 social network users on Facebook is less than the total user base, the entire population size, all social network users on Facebook. And this was in the year 2015. It was gigantic in 2015, even back then. So yeah, we would have met that 10% condition with this sample for sure. We took a sample size that was, say, like 2 million, that would have been crazy. But then that condition might not have been so reasonable. Well, maybe it passes, but we'd have to use further information to know for sure. So yeah, the sample size N matches up with the 10% condition as well. As far as the randomization condition goes, let's see. Report 56% people participated in a survey of social network users, so it was not okay to friend his or her boss. Never said we had a random sample. It said here, p hat based on a random sample of 50. So if we really grab a random sample, we'd have said we meet the randomization condition. So that's kind of the look at how this problem would have went. Yeah, go ahead. If they lose the part simple random and they just say a random sample, we'll allow that to qualify as well. But that's another one of those gray areas in statistics where sometimes you do have a random sample, but it was guaranteed not a simple random sample. That a bunch of the statisticians that did the study come together and they say, when we analyze the random sample we got, it's close enough to qualify to be a true simple random sample. But that takes a whole slew of experts. And one context where that comes into play is when we were all the way back in, say, chapter 2. Let's see. Quantitative variable in chapter 2 is what we're looking for. And there's one particular problem we're going for. This one. Oh, just had it. The Pacific bluefin tuna off the coast of California. It was a random sample. But how do you get a simple random sample of Pacific bluefin tuna? You have to identify every single Pacific bluefin tuna in the Pacific Ocean. And that is a big place. And these fish migrate from Japan to California pretty rapidly, it turns out. It's impossible to list every single Pacific bluefin tuna and take a simple random sample like we did with our Excel trick. Can't be done. So now you need to take the statisticians that got the random sample, compare them with ocean experts, ecology experts in biology, and say, would this have actually qualified to be effectively a simple random sample based on how we caught the fish? So much you'd have to talk about just from that alone. If it says random sample, we'll allow it to qualify based on our conditions because we realize we can't answer everything based off these conditions here. Our riots are just too short. So just saying random sample is good enough for us as well. Other questions at the moment? Okay, well, thanks for all these questions so far. These are the right kind of questions to think about when it comes to statistics. That's also kind of answering the question why there is really big money in this field. If you're looking for a line of work to go into, compare or complement it with statistics, and that's a great degree plan because there's a lot of work to be done in this kind of field. This kind of stuff is hard. It's hard to get done exactly right. And you're always going to be finding work if you have even a minor in statistics. But we'll come back to here, look into the conditions next class, and probably even start section 13.3. Have a great night, folks. We'll get back to it on Thursday. All set?
I think so.
Awesome, thanks. Yeah, that was a good question about the double negative on that one.
Yeah, I wrote it, but then I connected it to my Greeks, it just sounded not good,
Yeah,
so. All right, man, we'll see you tomorrow.
yep, see ya.